In this video we're going to look at differentiation. Here I've drawn a curve y equals x squared. And what if I wanted to find out the gradient at a particular point? Just say here, or here, or here, or here, or here, or here. Well, as you can see, the gradient is going to change depending on where you are in this curve. Because it's a curve, the steepness is changing. Here it's quite a large negative gradient. Here it's a negative gradient. Here the gradient would actually be equal to 0. It's not changing height here. Here it's positive, here a bit more positive, and so on. Well, let's just focus on this particular point here. Well, if I wanted to find out the gradient at this particular point, that's the same as the gradient of the tangent at that point. I've just drawn a tangent to touch the curve at that particular point. So the gradient to a curve is the same as the gradient of the tangent at that particular point. So let's have a look at working out the gradient of the tangent at a particular point of a curve. So let's just say here I wanted to work out the gradient at this particular point. Well, I've drawn the tangent. The only thing is I don't know any points, apart from one point, I don't know any other points in this tangent on the line. So what I could do is actually, I could work out the gradient of a chord. So I could choose the point on the curve and another point on the curve, and I could work out the gradient of that chord. And as you can see, as I bring the chord closer and closer and closer to the point where I want to work out the gradient, the chords get more and more closer to being parallel to the tangent. So let's actually work out the gradient of some of these chords. Let's just say, for instance, I want to work out the gradient of the tangent here. Okay, so I want to work out the gradient of the tangent at 2, 4, at the coordinate 2 across, 4 up. So what I've done is I've just chosen a point on the curve, 3 across 9 up, okay, 3 squared is 9, and I'm going to work out the gradient of this red dotted line, this chord. So the gradient, remember, is y2 minus y1 over x2 minus x1. Well, y2 would be 9, subtract 4, and I'm going to divide that by 3, subtract 2. And then that would give me 9 subtract 4 is equal to 5, and 3 subtract 2 is equal to 1. So the gradient of this line is 5, which is quite large. Let's bring it a bit closer, okay? So let's try this particular point here. So instead of being 3 across, I'm only going to go 2.5 across. So 2.5 squared is 6.25. So let's work out the gradient. 6 off this red line, this red chord. 6.25 subtract 4, that's y2 minus y1, over 2.5 subtract 2. And whenever I work that out, that gives me 2.25 divided by 0.5, but then that would be equal to 4.5. So as you can see here, the gradient's getting less steep, okay, for this dotted line, and it's getting closer to the steepness of this black line, the tangent, at the coordinate 2, 4. Let's make the chord even closer. So this time, I'm going to go a tiny distance across. I'm going to go across 0.01, so I'm going to go from 2 to 2.01, and 2.01 squared is 4.0401. So let's work out what the gradient of this red line would be. So it's going to be 4.0401 subtract 4 over 2.01 subtract 2. Whenever I work that out, it's going to be, top line is going to be equal to 0.0401 divided by 0.01. And whenever I work that out, that would be equal to 4.01. Now, as you look at the gradient of these chords, it's gone from 5 to 4.5 to 4.01. And as you bring this closer and closer and closer to this point, the gradient will get closer and closer and closer to the gradient of the tangent, which, looking at it, probably is 4. So the gradient is equal to 4 for this line. Okay, and the thing is, this is quite a time-consuming method of doing it. Let's actually do it. And what if I wanted to change the point? So let's do it for any point in this curve. So what I'm going to do is I'm going to choose a particular point, and I'm going to call it x across. So x across, and I'm going to its height would be, well, x squared is x squared. I'm going to choose a point across a tiny amount. Let's call that tiny amount h. So if I go across that tiny amount h, it would be x plus h, a tiny amount across. And the height, remember, I'm going to square this to find the height. So that's going to be x plus h squared. So let's work out the gradient of this chord, this dotted blue chord, between those 2 points. And let's pretend they're really, really close together. And remember, it's because it's x and x squared, it could be any particular position on this curve. So y2, which would be x plus h squared, subtract y1, which is x squared, over x2, which is x plus h, subtract x1, which is x. And let's work out what that would be. So expanding this brackets, remember, x plus h bracket x plus h, expanding that would be x squared plus xh, or hx, plus, let's go for xh again, I've got this the wrong way around, hx, plus h squared. And let's just switch these around, so x squared plus hx plus hx plus h squared. And then these would be x squared plus 2hx plus h squared. So the top line becomes x squared plus 2hx plus h squared, and I'm subtracting x squared. And that's all over x plus h minus x. Now on the top line you will see that the x squared and the x squared will subtract to give 0, and the x subtract x would also cancel out. So we're going to be left with 2hx plus h squared all over h. So let's divide through by h. So h, and h will cancel, so we're going to be left with 2x plus h. Now we wanted to go over a tiny amount. And as we bring this point closer and closer to it, in other words, as that tiny amounts get closer to 0, our answer gets more accurate. So let's pretend, or let's say that h is getting closer to 0. That means that our answer, you would get 2x plus, and a number that's getting close to 0. So that means that our answer would be 2x. This would get so close to 0, we could just ignore it. So that means that the gradient at any particular point on this curve is 2 times the x value. So if we go back to that previous example we had, the gradient here, well, the x value was equal to 2, and well, we had 2 times x is equal to the gradient of the tangent. Well, 2 times 2 is 4, and that was the gradient of this line, this straight line, this tangent, 4. Okay, so this means that if I wanted to work out the gradient at this particular point here, this tangent, well, I would do 2 times the horizontal position. Well, x is equal to 0. 2 times 0 is 0, and as you can see, the gradient of that tangent is 0. If I had the coordinate -1 and I wanted to work out the gradient of the tangent at -1 there, I would do 2 times -1, so it means the gradient of the tangent would be -2. If I choose a point over here, just say x is equal to 5, well, the gradient of the tangent there would be 2 times x, so 2 times 5, which is equal to 10. So that means we can now work out the gradient of the tangent at any particular point of the x squared curve really easily, because we have done this process. Okay, so let's just say I want to do the same thing for the y equals x cubed graph. In other words, I want to find the gradient of the tangent at any particular point on this curve. So the horizontal position is x, and x cubed will be the height, so that's x cubed. And let's choose it to point a tiny distance across, so x plus h. And then whenever you cube that, it would be x plus h cubed. Okay, and let's just work out the gradient of that chord. So again, it's y2, x plus h cubed, subtract y1, x cubed, over x plus h, subtract x. Now let's expand this, so we're going to have x plus h, x plus h, x plus h. Okay, and then you would expand this, so expanding the first bracket would be, as we have seen earlier, x squared plus 2hx plus h squared. And then you would expand this and simplify it, and if you'd done that, you'd get x cubed plus 3hx squared plus 3h squared x plus h cubed. So that's what that would be if you expanded it. So on the top line, we're going to get x cubed plus 3hx squared plus 3h squared x plus h cubed, subtract our x cubed. And then that's going to be all over x plus h subtract x. Now again, you will see those those terms will cancel, and on the bottom line they will cancel. So we'll be left with 3hx squared plus 3h squared x plus h cubed all over h. So let's cancel that out. So the h's cancel, and then you're going to be left with 3x squared plus 3hx plus h squared. But as we said, h is getting closer and closer and closer to 0. So it tends to do 0. So that means that this will tend to 0 and this will tend to 0. So they will have very minimal effect on our answer. And that means that the gradient of any particular point on the x cubed graph will be 3x squared. Now this process of going from the curve y equals x cubed to the gradient is called differentiation. And the notation is dy by dx. Okay, and that stands in the change in y over the change in x. Well, have you seen we're working out the gradient, dy by dx, the change in y, the change in x. So that means that dy by dx is equal to 3x squared. So to differentiate it, let's have a look at what happens. Oh, just before we do that, this is a formula which you may see for what we've just been doing, okay? And it's in the dy by dx, the differential, when we differentiate, that process of going from the equation of the curve to its gradient, that process is called differentiation. Differentiation. Okay, so going from the curve to its gradient of the tangent is called differentiation. That process, what we've been doing, you could maybe see it like this, and what it's saying is, it's saying that delta x, instead of using h, delta sometimes means a very small amount. So as you go across a small amount, rather than doing x plus h, you could do x plus delta x, subtract, so the function of that, so that's the height, subtract the height whenever it's equal to x, that's just what we've been doing, over delta x. Now as you notice, we always had h on the bottom line here, okay? You always had h on the bottom line, that's where the delta x comes from. So this is another version of the formula, and you find the limit as delta x tends to 0. In other words, as our h tends to 0, okay? So that's just another way of doing what we've just done. Okay, now as you do that for some curves, this is what you find. So if we do it for x squared, we get 2x. As we differentiate x cubed, we get 3x squared. As we differentiate x to the 4, we get 4x cubed if you were to do it for that. If you were to do it for x to the n, you would get n x to the n minus 1. So that is how this is the process of differentiation. And a really common thing that you're going to be doing is, a thing that you're going to be frequently doing is differentiating x's with a power. And what you do is you bring the power down and you reduce the power by 1. So that's the process of differentiation. So if I had y is equal to x to the 7, whenever you differentiate it, you get that dy by dx is equal to 7x to the 6, bringing the power down, reducing the power by 1. And this is great because it means we can work out the gradient of any particular point on this curve by taking the horizontal position, the x coordinate, doing it to the power of 6, and times it by 7. Have a look at the other videos in differentiation to see this in practice.